Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to look at row echelon form and rank. So in this topic, we will define row echelon form for an augmented matrix. We will then define the rank of an augmented matrix, and we will consider some consequences. First, to begin with a definition. A fleet of ships is said to be moving in echelon if each subsequent ship is behind and to the same side of the preceding one. This allows the fleet to more quickly respond to a threat, in this example, to the right of the direction of movement. For example, during the Battle of the Nile, here we see Nelson's ships moving in echelon to better respond to a threat to their starboard posed by ships of Napoleon. Starboard is right in the direction of movement of a ship. Now, an augmented matrix is said to be in row echelon form if all non-zero rows come first, followed by all zero rows. And also, each successive non-zero row must have more leading zeros than the previous non-zero row. For example, here we see an augmented matrix that is in row echelon form. Row 0 has no leading zeros, row 1 has 2, row 3 has 3, and row 4 has 5 leading zeros. Here's another example. In this case, row 1 has, again, no leading zeros, row 2 has 1, row 3 has 2, row 4 has 3, and row 5 has 1. And the last row of the matrix is a zero row. Consequently, we can make some observations. First, no two rows can have the same number of leading zeros. For if two rows had the same number of leading zeros, it would not be in row echelon form, for the subsequent row must have more zeros than the previous row. It cannot have the same number of leading zeros. Any column can contain at most one leading non-zero entry. And you'll recall that a column is said to contain a leading non-zero entry if any of the entries of that column is the leading non-zero entry of one of the rows of the augmented matrix. Here, for example, the entry at index 23, which is 5.5, is a leading non-zero entry in column 3, for it is the leading non-zero entry of row 2. Similarly, in position 4, 6, we see 0.8, and that is a leading non-zero entry in column 6, for it is the leading non-zero entry of row 4 in that augmented matrix. Also note that the zero augmented matrix is already in row echelon form. Finally, an augmented matrix in row echelon form must be upper triangular. Also, if A has either of the following two properties, A is a square diagonal matrix with no zeros on the diagonal, or A is a square upper triangular matrix, again with no zeros on the diagonal, then the augmented matrix must already be in row echelon form for any target vector B. For the vector B must be of the same dimension as A. If A is n by n, then any linear combination of n vectors must be an n-dimensional vector. Consequently, B must contain as many entries as any column of A. For example, here we see the matrix AB, where the matrix A is a 4 by 4 diagonal matrix with no zeros on the diagonal. We also see that it is in row echelon form, and it would be in row echelon form regardless as to what the target vector B was. Similarly, here we see a matrix A that is an upper triangular matrix. The matrix A is square, and so in this case the target vector is the 0 vector, but again, that must already be in row echelon form, for every single subsequent row has one more leading 0 than the previous row. This matrix is in row echelon form, for rows 1, 2, and 3 have 0, 1, and 2 leading zeros. This matrix is not in row echelon form because rows 3 and 4 both have 2 leading zeros. This one is not in row echelon form because rows 3 and 4 are 0 matrices, but they come before row 5, which is a non-zero row. We've already seen that this matrix is in row echelon form. By setting one entry on the diagonal to 0, the matrix is no longer in row echelon form, as both rows 3 and 4 have 3 leading zeros. Now, other mathematics courses on linear algebra sometimes require that each non-zero row be divided by the corresponding leading non-zero entry. This makes each leading non-zero entry a value of 1. This is inefficient from a computational point of view. It is not necessary in this course. If you do it, you will not lose any marks, but you will be wasting your time. And when we get to the unit on LU decomposition, you will understand why this is a waste of your time. You may even be made aware of, by some well-intentioned tutor, of something called reduced row echelon form. This requires even more work on your part. And again, you will not be losing any marks, but you will be wasting your time. Now, given a matrix A and a target vector B, if the augmented matrix AB is in row echelon form, as for example below, the rank of the augmented matrix is the number of non-zero rows. So in this example, we would say that the rank of this matrix is equal to 4, as there are 4 non-zero rows. The rank of the matrix A, on the other hand, is the number of non-zero rows if we ignore the rightmost column, that is, the target vector. So, if we ignore that last column, then we see that the rank of A itself is equal to 3. Some examples. Here is an augmented matrix. The rank of this matrix is 3, as there are 3 non-zero rows. Thus, we would write it as follows. If we ignore the target vector B, then the rank of the matrix is still 3, as there are 3 non-zero rows even if we ignore the rightmost column. If we take a look at this augmented matrix here, once again, we see it is in row echelon form. The rank of the augmented matrix is 2, as there are 2 non-zero rows, but if we ignore the target vector U, the rightmost column, the rank now is only 1. So thus, the rank of the matrix comprised of the first 2 columns, or the 6 by 2 matrix, the rank of that matrix is equal to 1. Now, if the augmented matrix AB is in row echelon form, then the rank of AB must either equal the rank of A or equal the rank of A plus 1. For example, here we see a matrix where the rank of the augmented matrix is equal to the rank of the matrix, which is equal to 3. However, if we set that next entry in the target vector to be non-zero, now the rank of the augmented matrix is 4, while the rank of the matrix A is still 3. Now, here are some consequences of this definition. Try to convince yourself that these are correct consequences. First, if A is an m by n matrix, then the rank of A cannot be greater than the minimum of m and n. Also, the rank of the augmented matrix must be less than or equal to the minimum of m and n plus 1. Finally, if the rank of A is equal to m, then the rank of the augmented matrix must also be equal to m. Following this topic, you now understand when an augmented matrix is in row echelon form. You can identify augmented matrices that are in row echelon form. You understand the definition of the rank of a matrix, and you know that the rank of an augmented matrix is either equal to the rank of the matrix, or the rank of the augmented matrix is equal to the rank of the matrix plus 1. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!